Hi, everybody. Good morning. Good afternoon. Welcome to the next installment of our class on data in macro development and structural change. We are delighted today to have Jonathan Colmer, who's going to be talking about weather and climate data. Weather and climate data is an increasingly important topic in development topics and in sustainability topics that run much broader than issues in developing economies. Jonathan's an expert in this topic, one of the best young economists working in this field, and his work spans a variety of different topics, including climate and weather and energy, and all related to development topics. So we're delighted to have him teach us about data that's used in these in research on these topics. So as before, we'll do an hour lecture, and then we'll have kind of 10, 15 minutes at the end for Q&A. So some of you have been here before. I recognize some names, not all the names, but more and more names, and that's great. If you have questions, you can just type them into the chat, or you can type them into the Q&A, and we will try our best to answer them live. Sometimes if you ask a question, we might say, hey, great question. Do you want to ask Jonathan at the end? And you can, you don't have to say yes if it's not convenient. You're in a public place or whatever. But if you can give us an indication, then we can promote you to panelists and have you ask your question at the end. Others we may just answer it right during the lecture. Okay, so Jonathan, thanks again for giving this lecture today. Why don't you share a screen and take it away?
Excellent. Yes, thank you. Thank you for the opportunity to speak today. It's wonderful to be here with you all. So yes, as David said, I'm Jonathan Colmer. I'm an assistant professor at the University of Virginia. I'm an environmental economist. I also do work in development and growth and in that space. So my environmental economics is sometimes in developing countries and sometimes in developed countries. I've started doing increasingly more macro work as a wannabe macroeconomist. I guess the one thing I should say that I'm not going into this lecture is I'm not an environmental scientist or a climate scientist. I'm at most a hobbyist. I have a huge interest in this space, but I think it's important to think carefully about the science aspect of things in doing all of this. And have spent a long time thinking about it, but I'm not, in any way a fully fledged environmental scientist or, atmospheric scientist. So that being said, I am British, and so I have a great wealth of experience about talking about the weather, and so I assume that's why David asked me to give this talk. So I'm going to talk about climate and weather data, and as David sort of mentioned, it's an increasingly important part of our experience. Although has, in many senses, always been an important part of life in developing countries. But it wouldn't be possible to really talk about weather and climate without talking about climate change. And as many of you know, hopefully all of you know, the influence that we've had in terms of economic activity on our climate is, unprecedented at this point. This is a recent figure from the IPCC's 2023 report, and just the increase in temperature relative to pre-industrial periods has just shot up in sort of the last couple of hundred years, and really relative to what we might think of as absent the sort of anthropogenic fingerprint. Has sort of moved away from the trend. So this panel here on the right, climate scientists would sort of simulate what we would expect to be happening to temperatures absent anthropogenic carbon, and then that acts as a sort of what we might think of as counterfactual for thinking about drawing inferences about the observed pattern of and contribution of anthropogenic forcing. So large increases in temperature. This is, obviously a huge challenge and has a lot of depth of economic content to engage with, of how we deal with that. But a consequence, of course, is that the experience of climate change is incredibly local. We expect to see and are currently experiencing large increases in extreme heat. more intense rainfall, increasing wildfires, droughts, storms, and sea level rise. And so all of these factors are a consequence of the global challenge that we face, but are experienced locally. And of course, one wants to understand the extent to which the consequences are how those are distributed as well. So I'm going to talk a lot about the weather and side of things, but this is just sort of to set out the challenge that we face. This is a great plot from our world in data, of which, again, it's great to be able to highlight our world in data in a talk on data. It's just a wonderful website, and the work that Hannah Ritchie and Max Roser have done is really fantastic. But this sort of shows where emissions are expecting to go. Right, we're already there's a sunk amount of warming that we're already experiencing, and the consequences obviously expand beyond warming. Absent climate policies, we'd be expecting about 4.1 to 4.8 degree increase in global average temperature. Obviously, global average doesn't imply everywhere gets 4.8 degrees, but that's going to be distributed very unevenly in a way that is going to be important for growth and development. Under current policies, it's closer to 3 degrees of global warming. That is huge still. And then the pledges and targets that we're currently committing to gets us to about 2.4. And there's increasing concern that we may even have already crossed the 1.5 degree pathway. We've had a couple of years of very hot summers that have resulted in anomalies that are above 1.5. And so if that continues, then we'll be across that threshold pretty quickly. The important part from development and growth really is that it's very clear that developed economies are the ones that got us to this place, right, through the Industrial Revolution. But at this point in time, it's the case that low and middle income countries currently generate 2/3 of emissions, and that they are going to account for almost 100% of emissions growth going forwards. Most developed countries or high income countries, emissions are falling, but where they're rising and where the growth is going to come is where in low and middle income countries. And for good reason, these countries are trying to alleviate poverty, increase relative living standards. That's the game that we all play as development and growth economists. That's what we're wanting to understand. And so really the fundamental question that is being discussed in the space, and if you want to think of it more like in terms of there are two of the most important global challenges we face, like how do we reduce poverty and how do we mitigate climate change. And so thinking about how we balance growth and the externalities from growth and how we manage that is really, I see as one of the most important questions that we can engage with and answer, and hopefully try and answer going forward. So how do we decouple emissions from growth? Because we're not going to go down to the debate here, but degrowth does not seem like a viable option despite its vocal advocacy, right? It's the pie is not big enough to share and distribute. We need to grow the pie, but how do we do that without imposing additional externalities? And there are lots of opportunities through decarbonization. People have been pushing the idea of a sort of new industrial revolution. There are, of course, no guarantees that this happens, but the question then is one of how will low and middle income countries kind of catch up with this? Most of the innovation is going to come from developed countries, and so we need to understand the constraints to financing adoption of new technologies, how we transfer these, how we integrate them. And there are big opportunities with those decarbonization opportunities as well, because ultimately, given the global public good nature of climate change mitigation, it doesn't matter where emission reductions occur. And I encourage you to read the paper that Rachel Glenister and Seema Jayachandran wrote in the Journal of Economic Perspectives earlier this year, which was really about thinking about the opportunities and constraints to decarbonization. So that sets the scene from a climate change perspective. I think, if we're thinking about where weather and climate data sort of enter in and how those things can consider and affect growth and development, the simplest model one can just sort of write down is a production function, right? You can think of this as a starting point from a development or a growth accounting perspective. Why are some countries rich and some countries poor? Well, either it's because there are differences in endowments or there are differences in how we use those endowments, right? And so there are clear channels in terms of thinking about data generating processes through which we think climate change could affect labor through reducing productivity. On hot days, people are less productive. It affects health. It affects mortality. And so that's going to affect endowments of labor. It can affect capital through increases in natural disasters and capital destruction, increased depreciation of capital. And then there are potentially effects directly through efficiency as well, right? In terms of, as I mentioned, productivity effects and the like. And so one of the key open questions in my mind in this space is the extent to which there will be growth effects. And there's been a lot of sort of econometric but model-free evidence really on the sort of relationship between temperature and growth. And I think, there's a sense in which I think it's really important to try and match the patterns and trends that we see in the data, both in the climate data and the economic data, to sort of underlying models. And just, conceptually, I think there's more scope for growth effects in lower middle income countries, right? Developed countries, high income countries are basically growing through pushing the frontier out and innovating and to more of an extent, lower middle income countries are sort of that frontier is somewhat exogenous to them, and so they're more affected by shocks and other things. And so there's potentially more scope for growth effects in lower middle income countries, less scope, I think, in developed countries. But I don't think we have a good sense of this, and I think more structure and more modeling is required, combined with the existing empirical evidence that we have to try and better understand this. And so that's one key point. And then the second key point is really understanding opportunities for adaptation, right? Adaptation and how we protect and engage in defensive investments to mitigate the consequences of climate and weather is critical, but not free. And so thinking about those margins of adjustment and understanding the scope and potential for them is also another area that I think a lot of work can be done. I'm not going to spend any more time telling you what we know, but there was a great course this November through Bread and IGC, another virtual PhD course on environmental economics, and there are plenty of lectures that you can go and see there to sort of get a sense of the state of the art of the literature and what we know and sort of what questions yet we still need to answer. But yeah, I'm going to leave it there and move more onto just the data and side of things. So sort of a key point that I think is really important conceptually when thinking about weather and climate data is that weather is not climate. And so, of course, there's a huge literature that has estimated the relationship between economic outcomes and weather experiences and wanted to think about what that implies for climate and for climate change. The challenge there, of course, is that what happens in 2100 is going to be a consequence of a lot of change demographically, technologically, and otherwise. And so, those relationships, those marginal relationships may change over time due to adaptation or changes in exposure and vulnerability. And so one can't necessarily simply just extrapolate out. But the target or the parameter that we really want to understand and identify, right, is the effect of climate change. And this is where expectations become very important. There's a sort of quote, which is attributed to Mark Twain, that climate is what you expect and weather is what you get. And so understanding expectations is an important part of this. But there are different ways through which climate could affect weather. Weather is ultimately part of the underlying, is the experienced aspect of the underlying distribution that is climate. And so that could be captured through climate change could result in an increase in means. And so you get more hot weather and less cold weather. It could be just an increase in variance, which would result in more hot and cold weather, or increases in both the mean and variance, which would mean we would get more record hot weather and much more hot weather, but maybe less changes in cold weather because of that increase in variance as well. And so just how we conceptualize and think about weather versus climate, I think, is very important, especially when doing research, that we're not saying that weather is climate and climate is weather, and those things are important distinctions. So how we measure weather and how we've learned about the weather itself has a fascinating history. Like, for good reason, people have been trying to understand the weather for a very, very long time. If you go back to 650 BC, the Babylonians were trying to predict short-term weather based on appearances in clouds and optical phenomena. And the reason being, of course, is because they're trying to grow food, and the weather is very important for agricultural production. By 300 BC, Chinese astronomers had created a calendar which divides the year into 24 festivals, which are each associated with a different type of weather. So we've very slowly but surely been sort of trying to learn and get all this together. And at a similar time, Aristotle wrote the text Meteorologica, which provided a number of theories and ideas about the formation of weather. Aristotle wrote a number of books and with a number of theories about various aspects of life. And many of those theories were also somewhat erroneous, but the weather theories were also not necessarily holding not much water. But it took us a very, very long time in terms of scientific progress to sort of realize this. It wasn't until sort of the end of the Renaissance period and sort of the start of the Enlightenment where we tried to learn about weather and climate with more gusto. And so this period of the 16th to the 19th century were where many advances in our understanding of weather and meteorology really grew out. And this is through the inventions of different tools like the thermometer and the hydrometer, which is about measuring humidity, and the barometer, which is about surface pressure. All of these things and increasing in mapping and other things. The Beaufort scale, for example, for measuring wind speed was invented by a captain in the British Navy, and who did just a tremendous amount of sort of home science, so to speak, in terms of trying to map wind patterns and understand things for navigation purposes. And so, yeah, that's where we got to sort of a pretty core understanding of meteorology, and then of course advances in computation and satellites has just resulted in just an explosion of the availability of data and improvements in our ability to forecast the weather, which is obviously important. For again, many reasons. We were motivated to do this for agriculture in a sort of core sense, but for navigation, for military operations, understanding the weather and what it's going to be is important there, in public health, and then just more generally, as sort of inferred from the Enlightenment period, the scientific curiosity, wanting to understand the world. And so, I talked about and I motivated the talk from a climate change perspective, but the weather matters very much independently of climate change. Climate change makes it important and increasingly more important. But development economists have been talking about the weather for a really long time because unpredictable weather is just one of the most important risks that individuals living in rural agrarian societies face. And so weather and the measurement of weather and our understanding of it is critical for understanding the livelihoods of the poor and for understanding decision making and economic consequences in those settings. And so the key questions that people have engaged with are trying to understand how individuals manage risk and how expectations are formed and how we learn and what the barriers are to mitigating risks and how we can make investments and adopt technologies and what the constraints to technology adoption are and what sectors we work in. All of these things are kind of coming from a more agricultural sort of perspective, and Julieta has talked on this already, I believe. But yeah, I mean, so there's just a huge amount of work in development that weather fits into, whether your interest is in climate change or otherwise, right? We want to understand how the economic and policy environment hinders or helps the management of these risks, and then I think increasingly thinking from a more micro to macro perspective, what the aggregate consequences of these risks are as well, and how that then feeds into understanding the broader macro development question of why are some countries rich or why are some people rich and some people poor. And so I think, I'm trained as a microeconomist, but again, have aspirations and interest in the macro space as well. And David's I've been working with David and learning a huge amount from him in this space. But I think within the climate and weather space more generally, in my view, many of the remaining important questions are macro. And so this gets into thinking about how we take the very rich micro evidence base we have about understanding the relationship between economic outcomes and weather and think about the aggregation or the aggregate consequences of these micro estimates. Key questions then come into play about the role of general equilibrium effects, the fact that when we have these short-run elasticities, what that implies about long-run elasticities is where expectations become important as well. Many of the margins of adjustment we might think are important from a climate change perspective in terms of being forward-looking and making investments in education or deciding whether you're going to work in agriculture or outside of agriculture are like forward-looking and not really necessarily captured by a regression of that outcome on year-to-year variation in temperature, because we shouldn't be expecting people to make durable or permanent decisions in response to short-run fluctuations. And so how we grapple with that, I think, is incredibly important. And there's a huge, I think, opportunity for macroeconomists and macro-minded people to sort of impose more structure on the problem, to try and make some progress in this space, and sort of reconcile the micro and macro literature. I think, as is it's an evergreen statement, as is true in all sort of economic research. I think it's really important that we understand aggregate patterns and trends and make sure that the models and evidence that we have is sort of matching to these. And then, of course, increasing amounts of work in sort of the micro to macro space means that, the huge body of literature on sort of micro weather and micro climate research really opens up opportunities for sort of moving out in that direction. And just pointing to the adaptation point I raised earlier, like taking beta hat and multiplying it by the change in temperature in 2100 is a thing you can do. But I think that the real rich and interesting economic content, now that we've established that this is an important problem to engage with and solve, is understanding more about the transition path. What are the margins of adjustment that people are going to engage with, and how is that going to affect the mapping of weather and climate into damages? That seems to me the critical point. So, in terms of the data itself, how do you go about working with weather data? What are the different sources? And if you have a research project that you're wanting to do where you want to understand some intersection between economic activity and the environment, you need to get weather data. And the challenge is that there are many different opportunities and many different sources of weather data that you can use. And so it's not always straightforward and easy to pick. And that's, I think, in part why we're having this lecture today. I've spent a lot of time thinking about it and grappling with those challenges. And so hopefully this becomes a useful resource for others who are sort of setting out in this space. And so the key challenge with weather station data is that access to information is not equal. There's just a huge amount of variation in the distribution of weather stations themselves, the quality of data, and even the ability to access it both within and across countries. So if you try and contact various meteorological departments in different countries, some are more responsive than others and may be willing to give you the data. Others, no, they aren't. And so it becomes a challenge to sort of think about the best way to access this. One of the things that is well understood within the distribution of these stations is that there's a strong urban bias. This is somewhat driven by developed countries more so than low and middle income countries, just because there are more stations in high income countries. But this means that that's an important, where these areas are located and where they're measuring the data is an important thing that one has to account for. There's good historical data in some countries, but not otherwise, and so this becomes important when measuring the variables we care about. And the measurement of this data is not exogenous to what's happening on the ground politically and in terms of economic activity. There's a demand for this information, and when demand is higher, there is more information, and when demand is lower, there's less information. But events, conflicts result in large gaps in the record. So the Rwandan genocide, for example, resulted in a loss of 15 years of data. And I think really the core point to make here, especially when it comes to thinking about the research aspect of things, is that one of the reasons weather data is used, I think, so widely is that it's a nice realizations of weather is a sort of provides nice exogenous variation, right? It's not endogenous to what's going on the ground, but the measurement of weather data is not exogenous, right? And so if one's wanting to understand the relationship between rainfall and conflict, and you have a cumulative variable like rainfall where you're counting the amount of rainfall over a given period, and people stop collecting rainfall data during conflicts, then you're going to have this endogenous measurement where there's going to be less recorded rainfall when conflict is going on and more rainfall when conflict isn't going on. And so that becomes a challenge from an inference perspective. And so I think one of the key messages that I hope comes across from this is that, whilst realizations of weather might provide a nice source of exogenous variation, one has to think very carefully about the measurements and the collection of that data. So, some calculations that we did just using the existing weather station data. We just got information on where weather stations are, and we restricted to the weather stations that are recording information on temperature and precipitation as most commonly used by economists. And if you just sort of look at the correlation between where these stations are and sort of GDP per capita through the Penwell tables, you see that there's a pretty strong relationship between income and the amount of data that exists. Developing countries, low and middle income countries have far fewer weather stations than in high income countries. And that's just in terms of like whether data is being collected. Like this isn't getting into the quality of the data, but that also becomes an issue. A further challenge is that there's been just a lot of change over time. Stations open and close. And you see here, the top line is in North America. The purple line is in sort of Australia and New Zealand and Oceania, that area. And the brown line is in Europe. Those lines are pretty stable over time. But looking at South and Central America, looking at Africa, looking at Asia, there have been substantial drop-offs in the number of weather stations over time. So the amount of information that is being collected is decreasing. And again, that means that the quality and the measurement of data is presumably worsening. And so these are all important things to understand about using weather stations. As a sort of tangent or sidebar, weather forecasting is obviously an important aspect of weather and for decision making. And there are differences in quality that weather stations and the existence of weather stations themselves obviously play a feature and a role in. But there are large differences in the sort of quality and usefulness of weather forecasting information across countries and how that changes over time. So I think this is a space, understanding the value and the benefits of weather forecasting is, I think, a particularly interesting area of research. Mark Rosenzweig and Mushfiq Mubarak have done some work in this space. There's a paper being presented at the NBR Summer Institute, which you can all watch on YouTube this summer by Fiona Burlig and Erin Kelly and Amir Jina and Gregory Lane, and I'm forgetting the last co-author, but apologies to them, but a really fascinating experiment being done in India, providing more frontier weather forecasting information and seeing how that sort of affects decision making in those spaces. So all interesting avenues, right? So that's where weather stations are a particularly challenging sort of context to work in. We'll sort of come back at the end to think about when they may be better to use or otherwise. But other sources of data are satellite data. There's been a talk on satellite data already. Obviously, the amount of satellite data over time has grown substantially. One of the benefits of satellite data is that it is not plagued with the issues of on the ground in situ measurement that we sort of see with observational data. But the challenge is that it's not necessarily measuring what's going on the ground in the same way, right? So much of the measurements that satellites pick up are based on radiance, and radiance is not precipitation and it's not temperature. And so there's a lot of assumptions that go in converting raw satellite data measurements into drawing inferences about weather and precipitation and temperature. Those assumptions existing are physical ones. They're based on the laws of physics, and so they're maybe a little easier to swallow sometimes than some of the assumptions we make in economic models. But the models that being used are improving over time, as our understanding of climate and weather improves as well. So the benefits of the satellite data is that you end up with sort of a much more consistent record over time and space, which is then available to use. But again, as with any kind of satellite product, you have to be concerned or at least aware of prediction error and model uncertainty. There's great work that's being done in this space. And where possible, sort of the combination of using satellite data and in situ observations can help to sort of discipline the satellite data in a way that helps to get a more accurate representation of on the ground experiences. So And that's what this figure here by some meteorologists has sort of shown. Um, there's a middle ground between station data and satellite data, which is known as reanalysis data. This is data that I have used most often, but it basically combines in situ observations and satellite data in sort of a best practice way as discussed, but with climate models as well. And so what this results in is, I would argue, a consistent best estimate of weather realizations over time and space. And the benefit is that you end up with data for every hour now at multiple different atmospheric levels. So on the ground and further up in the atmosphere, if that's what you want to do, which sometimes you do. If you're interested in thermal inversions, then you care about differences in temperature at the lower atmosphere versus higher atmosphere. And so this data is incredibly helpful. And what it basically does is to fill in the missing jigsaw pieces using, again, structural models, but based on the laws of physics. And that's what effectively these climate models are. And so the benefits of this is that the limitations are well understood by climate scientists in terms of the existing models and where they do better and where they do worse. And the biases are well known. Although, again, the biases are somewhat identified relative to the ground station observations. And if there are issues with those ground stations, then that becomes, that you don't get around that. That doesn't disappear. But what this results in is a more physically reasonable estimate of weather experience in places where there is low station density. But then the balance is that you are going to potentially smoothen the other way and result in potentially less accurate information in places where there's a good amount of station measurements, right? So if you're working in high-income countries which have maybe a very good density of stations and less of the maybe endogeneity issues that we might be concerned about in lower middle income countries, then there might be better reasons to use station data as opposed to reanalysis data. But increasingly, people are using reanalysis data, like the ERA5 data is the sort of one of the frontier data products in the space, and I'll talk a little bit more about that shortly. But that's one of the data sets that are increasingly being used for work in developing countries or for cross-country work, because you have this consistent best estimate over time and space. So I think sort of one of the key take-homes is that there is no universally correct weather or climate data product. You really have to think about what you need in your context and what the best or least bad option is. There's a great paper in the Review of Environmental Economics and Policy by Max Alfamer and co-authors, which provides a really excellent discussion of the trade-offs and more detail as to the points that I was raising. But yeah, more often than not, these days, the sort of type of data you're going to work with is going to be gridded data. It will either be sort of an interpolated data set of station data. So you may be familiar with UDEL or the best data, which is Berkeley Earth, or PRISM data in the United States, or reanalysis data, as I mentioned, the ERA5 data. And the interpolated data is easy to work with. It's simpler than the reanalysis data, and it works best where there's good station density. The reanalysis data I find is more helpful in developing country context. But again, you can't just sort of take the data and then just assume it's fine. Like, you want to think about the region you're working in and understand, and for example, what are the issues of using, say, reanalysis data in that context. Atmospheric scientists know what the biases and issues are when you're working with reanalysis data in India versus China versus Mozambique. And so understanding that for your context is an important sort of deep dive to do, I would suggest. And so yeah, you have to sort of figure out what data products are most appropriate for the question and the area that you're working in. What variables do you need? What's the resolution that you need over space or time, and understand what the potential caveats are in the situation. So it's almost like a least bad rather than best sort of trade-off. And so just being aware and being transparent about the caveats is, I think, the important thing to do. A sort of a second sidebar is that working with precipitation data versus temperature data is like something that really needs to be thought about carefully. rainfall data and humidity data is just measured far worse than temperature. The reason being is that precipitation is just incredibly heterogeneous over time and space, right? And you know, this is true of people's experiences with weather forecasting as well, right? The temperature, when you look at the weather forecast, people are pretty confident that the temperature is going to be what the temperature is. But when you look at the weather forecast for rainfall, and it's like, okay, 20% chance, and what does that 20% really mean? And you know, it can be wrong. It doesn't rain, or it rains somewhere in the area, and you know, it's a much more complex thing. You know, it might rain on one side of the mountain but not the other, and so spatially rainfall data is just a harder thing to measure. Whereas temperature data is much more uniform over time and space. It's more spatially correlated, and so there's a sense in which broadly it can be interpolated with more confidence. There's also, you know, we know that the built environment affects temperature experience, and so, you know, things like urban heat islands kind of get in the way of that a little bit and result in more local variations in temperature, but not in any way the same scale as precipitation. And one of the sort of core take homes that meteorologists and atmospheric scientists would want you to know is that there's so much more uncertainty about hydrological variables. And even across products, you can get a sort of 40% disagreement on what average global precipitation is. And you get weird correlations and weird patterns. And so you just have to be super careful when working with rainfall data. I think many meteorologists and atmospheric scientists would just rather we didn't use the rainfall data versus temperature. So for the type of inferences and analyses that we're doing, just because there's just far more uncertainty in this space. So in terms of how you go about processing it, because that's, I think, one of the biggest barriers to entry to using this data. You know, working with gridded data is a really useful start, and sort of helps to make things a lot easier. And so, you know, you start with the climatic data. Then you obviously have some shapefiles of administrative boundaries of interest, like a country or state or districts or counties that you're working with. And so sort of the intersection of those climate data and shapefiles is really important, and how you aggregate those. And then you might want to weight that data to sort of think about variation in land use or population. So when we work with this data, multidimensional data is the type of way that we store climate data in arrays, and they're normally known as NetCDF files. And when I first started working with NetCDF files, I was like, I had no idea what they were or how they worked, and it took me a long time to figure it all out. One of the nice things about them is that they're self-describing, so all of the metadata is provided as part of the file content, which means you have all of this information about the data structure and content. But then the way that you should think about these is that for a given atmospheric level, so let's just think about the surface, the data are basically images or rasters effectively, which get stacked over time. So you have latitude, longitude, and then hours that go throughout over time. So you have temperature in every hour or precipitation in every hour, and then that's assigned along those dimensions. And so that's a non-trivial data set to work with, right? Because you have to unpack that and organize that. You can't just read that into Stata and just kind of get on with your analysis. It's too complicated. And so for any given project, you need to sort of think about first, what is the type of data you're going to work with? What temporal scale are you going to be working at? You're going to be working with daily data or monthly data or annual data or multi-year data, taking averages or moving averages over 5 years or 10 years, right? And that's often going to be constrained by the economic data that you're working with. But then you need to think about what regions you're working in. Are you going to work at sort of the district level, or are you working at the state level, or are you doing things across countries? For aggregating that data, right, starting from this gridded data product, which is hourly, right? You go to the annual, year or day, and you go from the cells, which are sort of much smaller than counties, to the county level or to the state level. And are you going to weight that by population or the sort of the area of the country that is engaging in agricultural activity, if you're interested in that sort of side of things? It really depends on sort of the economic questions you're working. And then one of the really important things, and again, an important take home, I think, is that non-linearities and extremes are really important in this space. Like average temperature is really sort of not what we think of as the way to think about it. A good example is that the average temperature in New York and San Francisco is sort of very similar. But New York is hotter in the summer and colder in the winter. And so like those experiences of weather are going to be very different. And so what's happening in the tails of temperature, like in terms of hot and cold, are very important. And so more often than not, what you want to do is construct sort of these nonlinear variables at the cell level and then aggregate rather than aggregating all of the data and then doing a quadratic of the country level average. Sorry for some background noise. If you can hear this, I'm in a hotel, and so there's some things going on in the background. So one of the things that we've been working on is a new tool, and there's a new Python package being designed by Dylan Hogan, who's a PhD candidate at Columbia University, and is just an amazing job of putting together the sort of an efficient script, effectively, that will walk you through these stages and sort of implement them at relatively low cost, right? So you have to make those initial choices, but once you've made those parameter choices, you press go, and the goal is that this will aggregate the data over different spatial and temporal scales. It will do secondary weights if you want to, and you provide the weights or the data for the weights that you have. And it's just done it results in a very computationally efficient and memory intensive. It addresses the main barriers to entry, in my view, like the things that those who were working in this space in sort of the early days had to figure out for themselves and do in various different ways. We're trying to avoid reinventing the wheel over and over again. And so this will allow you to also construct a number of different variables and functional forms, which is very helpful, again, if you're wanting to do those nonlinear transformations at the cell level before aggregating. And then what you end up with at the end is a panel of daily or annual or monthly data by the administrative units that you're interested in working. So we're putting together a bunch of documentations and worked examples for this, and using it to sort of generate the work with the different gridded data sets to see how it all kind of pans out. But we're kicking the tires, but it should be available for others to use going forward. And again, Tamara Carlton, who's someone else we've been coordinating with and having conversations with about this for the last sort of year or so, has been putting together a similar package in R for those that don't want to work with Python. And so this idea of going back, first taking the climate data, then putting in the shapefiles, going to the secondary weights, thinking about that, all of that process from the netcdf files through to the thing you can read into Stata or R is the goal. So this is the workflow for the program. So you load in the administrative regions shapefiles and the climate data. You have to make a decision whether you just want area weights or whether you want to have population weights you can get from the SACEN gridded population of the world, or agricultural area crop weights from FAO, right? And it will do the weights and the area weights and the secondary weights, and then transform and aggregate the data, and then you get this file at the end, which is can be merged with the Penwell tables or whatever data it is that you're working with along these sort of common identifiers into a sort of standard, more merge type of approach. So just to give you an example, so this is what one of those layers of a netcdf file looks like. So this is the temperature, 2-meter air temperature on the 1st of January 2022 at 1 a.m. UTC. You'll note that like the longitude goes from 0 degrees to 360 degrees. And so that is not normally the way that we sort of think about looking at the world map. Normally we go from like negative 180 to 180. And so that type of adjustment needs to happen when you're working with the data. And so transforming that is part of what the package does. It's not going to be a problem if you're working in the United States, because if you tried just doing this, you'd get back a bunch of missing variables because negative 100 and something doesn't exist. But if you were thinking, oh, I'm working in the Philippines, and you were using the value there, then you might end up getting the wrong inference on that. The data, so this is what the raw data looks like. It's very, very granular. This is the reanalysis data. It's on a 0.25 degree grid, which is approximately 25 kilometers by 25 kilometers at the equator. The Earth is spherical, and so the latitude changes as you go further north and becomes a larger grid cell. But yeah, this is how it sort of looks. And then, you would take your administrative boundary shape files. So here's the IPAM's national boundaries. You then click go, and you get the area weighted weather data. It's been converted from Kelvin into air temperature in degrees Celsius. This is just the mean, but you could create a number of variables, which I'll show you slightly shortly. So this would be just, using all of the days, all of the hours, that all gets processed and kicked out to give the annual average 2-meter area, 2-meter air temperature, which is area weighted. If you use secondary weights using the population, the gridded population of the world data, you can get, this would be the FAO crop data. You can get a sort of crop area weighted, so slightly warmer in Canada when you account for where people are doing agriculture. And then if you were to do population weighted, it looks like a bit more like this as well. So Greenland ends up being a little warmer as well, where based on where people are living. So this is sort of the product this is sort of the outcome you would get if you're doing things at the national level. I said weights can be a standard. The standard sort of default is just to sort of account for the area of the cells within the administrative unit. So like in the United States, for example, a cell is much larger in Alaska than it is in Florida. And so that's going to be accounting for the sizes of grid cells and then the intersection of boundaries to account for the fact that administrative boundaries may sort of intersect parts of cells. So that all gets addressed. And then, you could use the secondary weights depending on your focus of interest. And so the premise or the intuition for population weights would be that cells with more population are going to contribute more for contributing average temperatures than cells with fewer population. So the different measures that the current output that we have, you can get sort of the average temperature, mean temperature, the sum of total precipitation, the minimum temperature, the maximum temperature. You can construct polynomials up to nth degrees, which is a sort of common approach. You can do the degree days measure, which is commonly used in agriculture to sort of think about the sum of daily temperatures exceeding a base threshold. Binning temperature into different intervals, which is a very common way for thinking about nonlinearities. It gets us something, gets us closest to something which is as non-parametric for understanding the distribution as possible. But we can do cubic splines. There's a whole host of things we're trying to integrate into the things so you can decide what outcomes you want specifically. So that's sort of where we're at to in terms of the data and how it's sort of how you might use standard weather. I wanted to sort of just use the last few minutes to talk about natural disasters and sort of the data in that space. So I'm going to talk about tropical cyclones. Tropical cyclones are sort of one of the most damaging natural disasters and certainly more prevalent than many others. It's estimated that about 35% of the global population is affected by tropical cyclones, and this is sort of the generic term used to describe hurricanes, typhoons, and tropical cyclones. That the name convention varies based on which part of the world you're in. But these are large storms that form over the oceans, and when there's more heat, the intensity of these storms increase when they're formed. And that results in sort of physical damage and loss of life through very intense winds, heavy rainfall, and storm surges. And the kind of issues here when working with natural disaster data is that it's important to, again, work with physical measures of disaster exposure. The challenge is that if we rely on self-reported damages that data like the MDAT database uses, where you sort of see the amount of damage, that's going to be endogenous because number one, it depends on the stock of capital you have in the first place. But there's concerns about measurements and the quality of that, the reporting, and how that's changed over time. And so drawing inferences from that data becomes very problematic. And the other point is that there's just a lot more natural random variation to exploit when using physical measures because of the exogeneity in terms of where they happen to be formed over the ocean, and then the path that the cyclones take and their intensity is not being driven by reporting and economic activity on the ground. So the best sort of initial source of data for this is NOAA's International Best Track Archive for Climate Stewardship. It's the IBTrACS database. This is the most comprehensive collection of tropical storms worldwide. You can download this data by different storm basin. And so it provides information on the path of the storms, the minimum central surface air pressure, and the maximum sustained wind speeds every 6 hours. So it ends up looking like this. So this is the storm paths in 2019. And so this tells you where the storms are going. The challenge, of course, is that, hurricanes are so large, or tropical cyclones are so large, that you can have damage going, or experience of very high wind speeds that are not along the track itself, that are further off the track. It depends on the radius of those maximum wind speeds, but also on the decay of wind speeds as you move away from the eye of the storm. And so the way that we tend to work with hurricane or tropical cyclone data is to use wind field models, which again are a sort of structural model based on physics that tells us how wind speeds vary relative to the hurricane center and how they decay, based counting for the rotation of the storm and the physics that we understand about where winds are going to be strongest in terms of the rotational force, as well as the radial force as it moves away from the storm. And so there are packages to do this that account for it. But the wind field model that we've tended to use most on our own work is the Willoughby model. And it's a sort of very simple parametric model of radial, which is how wind speeds change as you move away from the center, and azimuthal, which is just a delightful word, which is about how the wind speed changes as you move around, as you move around the hurricane at a distance that's fixed. And so the premise with the azimuthal wind profile is that the northwestern quadrant of the hurricane is where the wind speeds are most strong because of Coriolis, and then the sort of southeastern component is weaker in terms of how things go. And that's influenced by, as I say, the Earth's rotation, by storms motion, and various other factors. And so it results in this simplified but accurate representation of the wind field of hurricanes, which means you don't have to rely solely on just the maximum wind speed for the storm and the track where it goes. And there are basically just a few parameters that go into that. You have the maximum wind speed, the radius of the maximum winds, which comes from the surface pressure as well, and then a couple of shape parameters that basically just think about the exponential decay from wind speed as you move away from the center of the storm. So just to give you an example of how this looks, this would be the wind profile for Hurricane Katrina. This is the storm track. If we were to apply the wind field model, you see that there is some action happening, not just directly on the path itself, but even the radius is pretty big. It decays once it hits land. You have to account for ocean versus land speeds, and then it sort of, you have this. I don't know whether you can see it very well on the thing, but there is a pretty substantial band of non-trivial maximum wind speeds away from the center of the storm. We would then clip that to the land. And then if we were to do this for every storm in 2005, this is how it would look like for the United States. And if we did this for every storm between 1969 and 2019, it would look like this, right? So that's, you have all of these, you see that wind speeds dissipate quickly as you sort of move inland, but this shows you there's just a lot of variation in terms of exposures. So that's just maximum wind speed. An alternative measure of exposure that we like to use is known as the sort of amount of energy that is dissipated from storms. And this is different from maximum wind speed because it accounts for the fact that, storms that are moving more slowly and stay over a location for a longer period are just dissipating a lot more energy than storms that are moving quickly over a place. So they're exposed to these wind speeds for a lot longer. It also allows us to account for multiple storms within the year rather than the max across all storms. And this relies basically on like this power rule that's well understood within atmospheric science, where basically the amount of damage or energy that is dissipated from a storm is approximately equal to the cube of maximum wind speed. And so we calculate the energy dissipated in meters cubed per second squared by summing the energy over time within a cell. And that gives us something a little smoother, which gives us the sort of the amount of log of energy that is dissipated over this time period. So that's all I have for you today. But just to conclude, I think irrespective of climate change, but especially because of climate change, weather and climate are incredibly important to understand, and to understand them, we need to measure them to the best that we can for the context that we're working in. But they're very economically relevant and important, especially in lower middle income countries, for decision making and economic outcomes. there have been huge improvements in measurement and availability of data that you can take advantage of. But it's not just as simple as just taking the data off the shelf and just use it. You have to understand the data that you're using. You have to understand the physical foundations of it and how it's measured. And that measurement can be endogenous even when the physical realizations aren't. Accounting for these nonlinearities and these extremes is incredibly important, the literature has shown. And so just, yeah, I think that it's one of these cases. This is true of working with any data, but you have to think especially carefully about what the context is that you're working with and what data would be most appropriate. And unlike working with economic data sets where, you know, we might have more of a comparative advantage in understanding those limitations, you have to expend more effort and energy to really understand the environmental science components of things to make sure that you're using these data correctly. And then just be transparent about the trade-offs. And I think, you know, the hope is that the new data and new tools that we're putting together is going to make it increasingly easier to process the data. That's a blessing because, as I said, the barriers to entry are non-trivial, but it will also mean that people can process this data more carefully without necessarily having to dig into things and figure things out and understand what's going on. And so, again, I just caution to really think carefully about the data you're using and why it's appropriate for the work that you're doing. Thank you very much for your time.
Hey, Jonathan, excellent. Thanks for that great overview. Just one clarifying question. That AgFly, were you part of that? It wasn't clear whether you were being modest or whether you're just promoting the...
Yeah, so we've been working with Dylan. Dylan is the real rock star for AgFly. I mean, he's been doing a lot of the coding, but we've been working collectively with him and a team of pre-docs to sort of make sure it's working and debugging it. I like to think of myself as the dummy economist that's working with I'm the test dummy. So we've been working with Dylan, who's really an expert in this space, and not really just a hobbyist. So it's a team effort, but really the kudos goes to Dylan for the work that's been done in that space. We've just been helping him out and putting together a lot of the documentation and stuff.
And it's available for people to download, or it's kind of not quite.
It's not quite ready yet, but the reason, you know, Dylan is, as I said, he's an absolute rock star in terms of understanding all of this stuff. But what we really wanted to have was, you know, users that have some familiarity like me, and then, you know, we have RAs that have never touched this before,
right?
And we just want to make sure, like, across the spectrum of people who could be using this, that it means that, you know, if you wanted to use this, David, but have never downloaded weather data before, you could literally point and click and follow the documentation, and it would be easy to use. But yeah, and so like we're just making sure that in the event that you wanted to use it, that it doesn't all crash and burn when you first go, and that the assumed knowledge that someone like Dylan might inadvertently have has been accounted for by the test dummies like me.
Yeah. Okay. So it's in its final testing stages, and it'll be available at some point. If we wanted, we can ask Dylan. If we wanted, we could link to the. I'm sure people can Google it, but we could link to this, you know, to the CEPR, excuse me, page.
Yeah. The hope is that
later, because it seems like a great public good to actually, because you know, we're economists, we're not weather people. It's just like you said, we're economists. This is not a lecture on, you know, climate science, a lecture on how economists can use this. And so if we can skip the tedious stuff and go right to, you know, fraction of days in this spot that are above 50 degrees, that's really useful.
Yeah, no, exactly. I think that's the plan, and there will be the hope is the plan is to sort of be creating a product that is, you know, and a website and sort of user cases that people can then sort of access the different types of data. So it's more of a, you know, so this lecture can be linked to the website. We can link the AgFly to the thing, but the plan will be to create a sort of a website where people can see the sort of set of data sets that they could use and then use the AgFly and sort of best practices for economists is the goal.
Yeah, no, okay, that makes sense. Okay, so we have a bunch of questions. I feel like going in chronological order, actually. So Guy, do you want to unmute and ask your question first?
Sure. Thanks, David. Thanks, Jonathan. It was a great presentation and very informative. I had a question on on the number of stations. So in Africa, we see a sudden drop after 2000. It's not sudden, it seems systematic. And I understand you said wars, conflicts affect that, but it really looks like, it dropped and then stayed low. So I was wondering if there is any particular reason, or is it each station becoming more efficient, covering a lot of area? So I was wondering about that. Thanks.
Yeah, I mean, that is a great question. So I don't have a definite answer for you. I have some hypotheses. But I mean, I think part of it is that the increase in satellite data over time and reliance on that has meant that the need for in situ observations has maybe diminished more so than when satellites weren't available. I'm very encouraged to see my research assistant Nick nodding. That's sort of Nick is a real expert in this space as well. And so that's going to be part of it. But as we've discussed, there are trade-offs to using satellite data, and in situ data is very important for forecasting accuracy and for decision making. And so, but I mean, budgets, state capacity, it's an, again, like when thinking about developing countries and allocations of resources and limited budgets, how do you allocate those resources? Building a weather station is not necessarily going to be a priority. And so that's just sort of, I think, one of the constraints as well. Like there's going to be a whole magnitude of reasons. There has been some work, and one of the things we're going to do post lecture is to put together a series of references that people can sort of dig into. And there's a couple of papers that come to mind. I can't remember the authors that have described this pattern more generally. I should also caveat that the data that I used was from the GCHN database of weather stations, and so may miss some weather stations, but I think this is a pattern that is true across a number of the data sets. And the GCHN is I think one of the more comprehensive data sets. Yeah, Nick's saying that keeping weather stations going is expensive and data collection isn't always consistent. And so relative to satellites, it's cheaper and more accessible. And so that's part of it as well. But of course, you have to wait for the satellite data to become available, whereas the weather station data, you get it the day that you need it. So, yeah.
Okay, so that's kind of almost a perfect segue into the next question. Youngkyu, do you wanna ask your question?
But my problem, I think, is addressed. But I can ask again. Thank you, Professor Jonathan, for your presentation today. May I ask when satellite data can be useful for estimating the effects of climate change on economic growth? And what are the main advantages of using satellite data compared to other conventional climate-related data?
So I think one of the nice things about satellite data, right, is that it is granular in terms of space, and it sort of gives you a sort of a complete snapshot over the temporal ranges that you get. And so that gives you a good sense as to what the conditions are on average, although the more granular the better. Some satellites are coarser than others, right? I think the data itself doesn't answer the question of how one identifies the effects of climate change on economic activity. Like that's it's an input, but like one needs a research design, and actually, if you come up with one, let me know, because identifying climate change is a real challenge, right? Weather realizations are exogenous. Climate change is very much, or climate more broadly, is endogenous. It's a longer run phenomenon. Expectations matter, and so people are sorting and selecting along margins relating to that. And so that's a broader challenge. And whether you're using monitor data or satellite data or reanalysis data, the different sources that we discussed today. And I refer you to the Alfhammer et al. 2013 paper for the trade-offs along those things. But the data alone isn't going to solve the research design problem. It requires thinking about the underlying data generating process, what we think the economic model is that underlies that, and everything in between. So it's the data is an important input, and you have to think carefully about it, but you still need to. That doesn't solve the research design process, unfortunately.
Okay, thank you very much for your answer.
So I guess a related part of Youngkyu's question is kind of, to what extent are these types of data complementary? I was thinking about dust storms and PM 2.5. I don't know, I was in China recently and they were saying Beijing, the air has gotten better. When I used to live there, it was disgusting because of the dust storms and dust storms off the Sahara, the Sahel, those are a big deal. I mean, that's kind of climate data, but it kind of comes from a satellite. So it's not like there's a kind of strict
Yeah,
separation
and
between climate and satellite. Yeah.
yeah, so we use a lot of fine particulate matter data that comes from satellite products or reanalysis versions where you combine monitor data on pollution, satellite data on aerosol optical depth, which is how people sort of draw inferences about the amount of light that can get through the atmosphere. That's how you draw inference about sort of dust and particulates, and then chemical transport models, which are again structural models based on the laws of physics that talk about how pollution is transferred. So you can use these data sets to draw inferences about air pollution. You can use it to measure wildfires and crop burning. All of this stuff can, as long as it's on a gridded data product, which rasters are, that can potentially also be processed. But dust storms and dust is another thing. Again, wind data, not hurricanes, but the ERA reanalysis data, you can download wind speed and wind direction. And so you can sort of combine these data sources to think about where the dust is being pushed and from upstream to downstream. And so there's lots of nice variation that can be exploited to think about not just weather, but also sort of pollution as well. I mean, Beijing is the reductions in local pollution in China over the last decade have been insane. They've managed to achieve in a decade what it took the US 50 years to do. So it's still not great, but there are still the differences, the improvements in local air quality in Beijing has been dramatic, I think.
Actually, so I think it makes sense to have Momita. Do you want to unmute and ask your question? Is kind of on the same theme.
Yeah, thank you. So I was wondering if there's something in AgFly or otherwise that can help you figure out how to measure an extreme weather event, like for instance, a heat wave, without having to sort of rely on like government notifications of heat waves. Specifically, like if you can identify if a particular administrative district has like a lot of grid cells that have extreme weather events, but like I'm struggling with how I would define a heat wave, not, or how to identify it using tools that are already available through the reanalysis data in particular.
So the way that I would do that, and again, riffing, is I would take AgFly. I would process daily maximum temperature data, which would then give me and I would do that to the cell level probably, to keep things as granular as possible. So that would give me a stata file or a R file, right, which would be 365 days times like say if I was working in India, like I would have 365 days times a lot of cells, right? For so many years, but that would be probably still readable on like on a laptop of good quality. And then once you have that data loaded into Stata or R, right, you have a distribution for each cell. Like what the experience, how many days was temperature above 90 degrees Fahrenheit or above 30 degrees Celsius. And the way that I would think about heat waves is that it's not about the sort of the absolute value of the temperature. It's about the temperature relative to what people are used to. So, one could calculate the average maximum temperature for each cell. And then you'd have deviations or anomalies relative to that. And you could say, define a heat wave as when a day is above the 95th percentile or the 90th percentile of that location's temperature distribution. That is a hot day for that location. And at that point, I mean, so there is more convention here. There are papers that do this more thoughtfully. The way we've thought about heat waves is it's not really just about whether you have a hot day. A heat wave is more accumulation of hot days. So you could impose other restrictions, which would be like, oh, well, maybe we're going to define a heat wave as when there are 5 days in a row that are above 95 degrees Celsius. And so you'd have some trigger that would turn it on when you get above that 95th percentile, and it stays on and then it turns off. And so you would want to count the number, define a heat wave as like, did it stay on for 3 days or more, or 5 days or more? And so the AgFly data would aggregate all of the basic inputs that you would then use to model a heat wave. And then with that definition of a heat wave at the cell level, you would then aggregate to the district or the state or something like that, having done that nonlinear transformation. And that would tell you like, oh, what was the average experience of the heat wave in that location. So that's sort of how I would, think about the different parts. You'd start with the raw, like, how do we think about heat wave? Well, with temperature. There are different ways of modeling heat waves. You want to learn about that. I gave you a sort of rough sense of what one definition could look like.
Yeah.
Then you would use AgFly to process the raw data into a format that then allows you to more easily code up a definition.
Thank you. Yeah,
My
this
pleasure.
was very helpful. I also had another question, but I don't want to, like, it's okay if other people want to ask things.
So let's go to other questions, and then if there's time, maybe at the end you can come back. If not, you can email us.
Yeah, we're going to do a Q&A sort of write-up afterwards as well.
Thank you.
Sushil, actually, I don't see you here. Maybe you're not a panelist. Give me just 1 second. You've been a panelist before, but I guess you're not now. Let me promote you to panelist. And so whenever you're here, you can unmute and ask your question if you want, Sushil.
Hi, sorry, I've just joined. Yeah, thanks, Jonathan, for the presentation. It was great. I just had a quick question, which I think it was touched upon a little earlier, and also back to David's earlier point about, we want to take this data off the shelf and use it, but we kind of want to understand the limitations of it, particularly. And I'm thinking of the reanalysis data and the wind model data that you're talking about. So you said, they use structural modeling in some way, and I was wondering, are there papers or sources where you think we can read about this in a way that's kind of tractable to economists, if you have to think about these structural models?
Yeah, so I'm when I talk about structural models based on the laws of physics, I want to emphasize them being somewhat colloquial and try and give an economist mapping to what they do. I heard a great description of the way that sort of economists think about models versus engineers yesterday, where someone said when engineers or scientists, if they were going to do a model of the Titanic, it would be 100th of the scale and it would be perfectly defined, and you'd have the little deck chairs of the Titanic all perfectly sculpted, right? That's an engineer model. Whereas an economist model would be to take a milk carton and cut it in half, and sometimes it floats. And so it's sort of, economists get things down in a more reductionist way, right? Because models are useful and we get more simpler stylizations. The types of models that like atmospheric scientists and engineers are using are going to be way more detailed and way more complex, because there's a sense in which there's more scope for them to do so. They're not relying on behavior and other things, right? So it's very much based on laws of physics. That can be impenetrable to get into, especially if you don't have a lot of background experience in that. And I think that there are folks like Max Alfhammer, who's the origin of the model story, by the way. But the articles that folks that like Max Alfhammer and economists like Solomon Shang and Wolfram Schlenker and folks in the environmental economic space that have engaged deeply with the environmental science background and have environmental science backgrounds themselves more often than not. They write review articles like the one that I mentioned, and so that sort of provides a translation type tool. The other thing, though, one thing I would encourage you as a sort of best practice to do is to say, if you're wanting to use the ERA5 in India and you want to understand the biases and things, and of course, like you try and, how do you know what journals to look for? Because there are thousands and hundreds of thousands of journals, and you don't know what the good journals are and things like that. And it's different. There's also a different sort of attitude that economists have to journals that is not necessarily always a good one. but I would go to Google Scholar and I'd be like type in ERA5 plus India or something like that, or ERA5 plus India plus bias, and you will just because atmospheric scientists will have written hundreds of paper about learning about how ERA5 works in that context and what the biases are and what the limitations are, and that would just help you to understand the extent to which what are the potential issues that might come up. So that's like a useful, there's again resources that we'll share that will help you to navigate these sort of pathways and workflows as well.
Great. Okay, that's about all the time we have for today. I like the story about the model. We have the milk carton. Our milk carton's re-optimized though.
Yeah.
Like you change the environment and somebody says, hey, wait a minute, there's a big wave of COVID coming. Maybe I shouldn't go out to the Olive Garden tonight with all my friends and clean classes. And like the epidemiological models, there's just these brainless particles bumping into each other and you get this huge wave, of course, that looked nothing like what actually happened. The analogy to me is machine learning. You train a model, but it's a brainless model. It's every day David leaves at 8 o'clock to drive down Commonwealth Ave. One day, there's a holiday from school. What am I going to do? The brainless model would just say, I think he's going to go down Com Ave and the holiday. And no, that's not what I'm going to do on a holiday. And
although what I'd say though is that when with the atmospheric side of things, there's no people, right? And so it's less of a problem that the behavior aspects in there. Although one of the really fascinating things you see, and this is where maybe the biases and limitations come in, like if you just think about the atmospheric model, it can be super complex and is getting things right based on laws of physics. But there's been like really interesting things where you see like that if you have irrigation in a location, that affects evapotranspiration.
Oh, I see. Yeah.
And so then you have human behavior and activity that then reshapes the cycle in that location. Yeah. And so that can result in changes in surface heat and evapotranspiration. And so then you have this, which isn't in the climate models, where activity by humans on the ground influences that. And we know across not just the climate cycle, but across many different sorts of planetary considerations that humans have influenced those components. And so that then does feed into those the reality of those models, but is not captured by those models. And so that's like a really fun literature to dig into occasionally.
Yeah, no, that is. And I guess just the big picture, students, some are left, some have gone, but we're not going to beat those guys at their models. We're going to add economics into the mix. And I kind of just, if I were to forecast what a good economics dissertation paper would look like in relate to climate, it would, maybe probably have some people re-optimizing, but I can just, as a mechanical level, I imagine it's probably going to involve multiple types of data here. We talked about satellite data. Just, expectations are a big deal. A shock when you're expecting it is very different than a shock when you're not expecting it. And people's expectations are updating, but it's highly heterogeneous. I mean, how many of us would agree that the sea level is rising? Probably all of us. I bet you if you surveyed people in the world, there's many people who have no idea or don't believe it or whatever. And these expectations are really important. There's also the policy angle, like, there's droughts in India and Africa, and there's drought relief. And what are the chances it goes exactly to the right areas? It probably goes to the leader says, oh, my hometown, suffered a bit. Let me send the money there or whatever. You kind of know there's going to be implementation issues that are really relevant. In the climate science, they're never going to be thinking about these issues, well, maybe they are, but, we're going to have a comparative advantage in answering ththose kinds of questions as economists. So we're out of time. And, let me just, Despina, could you flash the classes? We kind of always end by flashing the subsequent classes. We're kind of running out of lectures here, but we have three great lectures coming up in the following couple of weeks. Meredith's going to talk about collecting your own data. Cheryl's going to talk about gender data, and Charles about time use data. These lectures are getting more and more complementary. Some of these extra data sets that that I'm referring to could be the other things we've talked about. Anyway, so I will see you everybody next Friday. And Jonathan, thanks again for the outstanding lecture.
Thanks for having me.
See everybody next time.